Okay, so in this video, I'm going to talk about one particular type of estimator which is more efficient than the OLS estimator when there is heteroscedasticity in the model. In the next couple of videos, I'm going to talk about two types of estimators. Those are most efficient than the OLS when there is heteroscedasticity. In the first case, we will know exactly the nature of the heteroscedasticity, and in this case, we could use weighted least square estimator. In the second case, the heteroscedasticity will be of unknown form, and we will use feasible generalized least square estimator. Okay, so we said that if there is heteroscedasticity in the model, then the variance of our residuals given all the x variables is not constant, rather it is a function of these x variables. So if we know the form of h of x, that is, we know what variable is causing this heteroscedasticity, we can use that information and incorporate that in our model so as to get more efficient estimates. For example, if we are regressing savings on income and these are our residuals, and we know that the variance of u given income, it is a function of income itself, as I showed you in one of my previous example, because we believe that it is the income which is causing this heteroscedasticity, which means h of x is this income. That is the sigma squared, it's a function of income. One way to correct this type of heteroscedasticity is to use this information. Because we already know that income is causing this heteroscedasticity, we can tweak our model a little bit to incorporate this heteroscedasticity. Let me show you how can we get this. So this is our error u. So what we can do is we can divide it by this function. In this case, it is income, and we're going to take the square root of it and then squared it up, and this will be equal to expected value of u squared divided by income. Now we know that this term is this and this. That is, there is heteroscedasticity in this term. So we will get from this sigma squared of the model income, right, this one. But since we divided it with income, so this term will cancel out with this term and we will be left out with the sigma squared, right? So our variance is unbiased in this case. In simple words, if we have the above model, what we can do is we can divide all the variables by the square root of income. We will transform our model and then estimate this new model, right? So this is exactly this will give you. So we can transform this model, and now we will be estimating this transformed model. Let's call this beta 0 star plus beta 1 star. This will be, and now this will be u star. What this model is doing is it's assigning different weights across different observations. So we know then that when we have heteroscedasticity in the model, if we draw a least square line, it goes like this. Now this is our low variance zone and this is our high variance zone, right? Because in this low variance zone, people with low income, they do not have many choices, hence their saving do not vary a lot. But people with high income, they may have more choices, so there is more variation in their income as compared with average income. OLS assigns equal weights across all these observations. So no matter the observation lies in the high variance zone or the low variance zone, OLS will assign an equal weight. But what this weighted least square does is it assigns different weights across different zones. For example, if an observation lies in this low variance zone, it will assign a high weight to it. And if an observation lies in this high variance zone, it will assign a low weight to this observation. Now this is different than the OLS, which was treating all these observations having an equal impact. But here, the weights and the impact of each observation depends on whether this observation lies in the low variance zone or high variance zone. So this is exactly what we are doing here, dividing our model by the source of the heteroscedasticity, we are assigning different weights across different observations. And this way, we are transforming our model, and then we are estimating beta 0 star and beta 1 star in this case rather than beta 0 and beta 1. Right, so in the next video, I'm going to give you an example in R using this method. All right, I'll see you in the next video. Bye bye.